Hello there, and welcome to Sleepy Science Vault. Glaciers are among the oldest and most patient forces on Earth. They do not form quickly. They do not announce themselves. They build, slowly and silently, across decades and centuries, layer by quiet layer, until something remarkable has taken shape beneath the surface. It begins with something as simple as snow. Snow falls on a high mountain, or across a polar plain, and unlike the snow in your backyard or on a city street, this snow does not melt come spring. It stays. Another winter arrives, and more snow falls on top of it. Then another winter. And another. Each new layer pressing gently down on the one beneath it, year after year, season after season, until the snow at the bottom begins to change into something altogether different. This is how a glacier is born, not in a single moment, but through the slow, accumulating weight of time itself. In those early stages, the snow beneath the surface transforms into what scientists call firn. It is not quite snow anymore, and it is not yet ice. It exists in a quiet in-between state, a dense, grainy material that has been partially compressed but still holds some of the openness of its original form. If you could hold a handful of firn, it would feel heavier than snow, more compact, with visible grains that have started to lose their delicate crystalline edges. Firn is roughly 2/3 the density of water. It still carries space within it, tiny pockets of air tucked between the grains, but those spaces are already beginning to close. As more snow accumulates above, the pressure increases, and those open channels between grains grow smaller and smaller. The weight of everything above pushes downward with remarkable patience. The air that once moved freely through the snowpack becomes trapped, isolated, sealed away in shrinking pockets as the material around it slowly solidifies. This process takes years, sometimes decades. Deep within the glacier, something even more subtle is happening. The individual snow grains, each one a tiny ice crystal with its own unique shape, begin to reorganize. Under sustained pressure and temperature, the crystals slowly restructure themselves, merging and growing in a process called recrystallization. The small irregular grains of the original snowflake gradually become larger, smoother, interlocking crystals of true glacial ice. It is a kind of slow transformation that happens entirely out of sight, in the cold and the dark, deep beneath the surface of the world. The ice that eventually forms this way is denser than almost anything you would find on the surface. The weight of the glacier squeezes out nearly all of the air, compacting the material until it becomes a hard, crystalline solid, far heavier and more ancient than the light snow it once was. And yet, some air remains. Deep in the oldest layers of a glacier, tiny bubbles persist, miniature pockets of atmosphere that were sealed inside the ice thousands of years ago. As the ice is buried deeper, the pressure increases around those bubbles, compressing the air inside them further still, preserving it in a state that scientists can one day read like a message from the past. The deeper you go in a glacier, the older the ice, and the greater the pressure bearing down upon it. Ice crystals in those deep layers can grow remarkably large over time, reaching sizes you would never see in ordinary ice, shaped by the slow, immense forces working on them from above. There is something quietly extraordinary about all of this. Every glacier you have ever seen, every vast, blue-white expanse of ancient ice, began as something as weightless and temporary as a snowflake. And through nothing more than time, and the steady accumulation of more snowflakes above it, that fragile crystal was slowly, irreversibly, transformed into one of the most enduring materials on the planet. Patience, in the world of glaciers, is not just a virtue. It is the very mechanism of creation. High in the mountains, or stretched across the poles in immense unbroken sheets, glaciers appear from the outside to be simple things. Solid, still, uniform. A wall of white and blue, ancient and unchanging. But that impression, as beautiful as it is, tells only a fraction of the story. Because inside a glacier, hidden from any casual view, there is a world of extraordinary complexity. A layered, structured, living archive that has been quietly building itself for thousands of years. Let us go inside. One of the first things that would surprise you, if you could somehow see deep into a glacier's interior, is the ice itself. Not its color or its density, but its texture. Because glacier ice is not made of the tiny, fine crystals you find in an ice cube or a winter frost. Given enough time, given enough pressure, the crystals inside a glacier can grow to remarkable sizes. In younger ice that is only decades old, the crystals are still relatively small. But in the oldest, deepest sections of a glacier, those crystals have had centuries to grow. They recrystallize slowly under sustained pressure, merging and restructuring, until individual crystals can reach the size of a baseball. In some of the most ancient ice on Earth, they can grow as large as an adult fist, smooth, interlocking grains that you could see and hold in your hand. It is one of the quieter wonders of the glacial world. That something as familiar as ice can, over time, become so completely transformed. And the transformation does not stop at the crystals themselves. The entire body of a glacier is layered, structured internally in ways that mirror the history of its formation. Each year of snowfall, each season of accumulation, leaves a faint record in the ice. Bands and strata build up over time, much like the rings of a tree, or the pages of a book stacked one upon another. Some of these bands record distinct periods of snowfall. Others mark volcanic events, layers of dark ash deposited by eruptions hundreds or thousands of years ago, now sealed permanently into the ice. Still others contain tiny particles of dust carried on ancient winds from distant places, preserved exactly where they landed, long before any human being was alive to see them. The deepest parts of a glacier carry something else entirely. As a glacier moves slowly across its bed, grinding across rock and sediment over centuries, it can freeze debris directly into its base. Fragments of stone, sediment, minerals, sometimes entire boulders, become incorporated into distinct layers near the glacier's floor. These debris-rich bands exist alongside clean, clear ice above them, creating a visible contrast in the glacial structure, dark ribbons woven through a field of white. This mixture of clean ice and debris tells a story of movement, of contact, of the long and grinding relationship between a glacier and the land beneath it. And then there is the air. Trapped within the ice, in tiny bubbles sealed away during the original compression of firn into glacial ice, are samples of ancient atmosphere. These bubbles preserve gases from thousands of years ago, carbon dioxide, methane, oxygen, in the exact concentrations they existed at the time the ice formed. For climate scientists, these bubbles are invaluable. They are direct samples of air from a world long gone, held in suspension, waiting to be read. The ice around those bubbles matters too. When glacier ice is very dense, when the compression process has squeezed out nearly all remaining air, the ice takes on a quality you would not expect from something made of frozen water. It turns blue. Not the pale or milky white of a snowfield, and not the dull gray of an ice cube, but a deep, quiet, luminous blue. This color is real, not a trick of light. Dense glacial ice absorbs the longer red wavelengths of light and allows the shorter blue wavelengths to pass through, creating that extraordinary hue in the oldest, most compressed sections of a glacier. It is one of the most beautiful things in the natural world, and it is invisible from the outside. You have to go deep to find it. Now, if you were to look at a glacier from above, or trace its outline on a map, you would notice something else about its structure, something more geographic than geological. A glacier is not uniform from top to bottom. It is divided, naturally, into two distinct regions. The upper part of a glacier, the high elevation zone where snowfall accumulates faster than it melts, is called the accumulation zone. This is where the glacier grows. Snow builds up here year after year, adding mass, feeding the slow downward movement of ice. Below it, at lower elevations, lies the ablation zone. This is where the glacier loses mass, through melting, through evaporation, through the calving of ice into water. In this lower region, more ice is lost each year than is gained, and the older, deeper ice of the glacier makes its way to the surface. Between these two zones, between the region of growth and the region of loss, there is a boundary. Scientists call it the equilibrium line altitude. At this invisible threshold, the amount of ice gained through snowfall is exactly balanced by the amount lost through melting. It is a point of perfect equilibrium, shifting up or down the mountain depending on climate, season, and year. When a glacier is healthy, when it is growing or holding steady, the equilibrium line sits lower on the mountain, giving the accumulation zone more room to build. When a glacier is under stress, when temperatures are rising and snowfall is declining, the equilibrium line creeps upward, reducing the zone of accumulation and giving the zone of loss a larger share. It is one of the clearest signals a glacier can send about the world around it. A quiet, structural message written not in words, but in geography. All of this, the layered bands, the ancient air bubbles, the debris-rich basal ice, the deep blue of the densest crystals, the invisible boundary between growth and loss, exists inside every glacier on Earth. Hidden from the surface. Silent and patient and extraordinarily old. You could stand at the edge of a glacier, feel the cold air drifting off its surface, and see nothing of this interior world. But it is there, in the darkness and the pressure and the deep accumulated weight of centuries. A hidden architecture, built by nothing more extraordinary than snow, time, and the slow, irresistible force of the earth itself. There is a common assumption about glaciers that is worth setting aside gently, right from the beginning. Most people, looking at a glacier for the first time, see something fixed. something geological and permanent in the way that a cliff face or a mountain summit feels permanent. They see a body of ice so vast and so still that movement seems almost incompatible with it. And yet glaciers move. They have always moved. They are moving right now, in every mountain range and polar region on Earth, flowing forward with a slowness that deceives the eye but not the instruments. A glacier is not a frozen lake. It is not simply water that has solidified in place and remained there. It is something closer to a river, one that moves not in seconds or minutes, but across years and decades and centuries. A river measured not in the rushing of water over stone, but in the slow, grinding, irresistible creep of ice across a landscape. Understanding why glaciers move, and how, is one of the more quietly fascinating chapters in the story of the natural world. The first and most fundamental reason a glacier moves is the same reason water runs downhill. Gravity. A glacier accumulates mass in its upper zones, where snowfall builds the ice thicker and heavier over time. That accumulated weight creates pressure, a slow, persistent force that is always seeking a lower point. And so the glacier, over time, responds to that force exactly as any fluid would. It flows downward, always downward, following the contours of the land beneath it, moving toward lower elevations at a pace so slow it is almost philosophical. But gravity alone does not fully explain the mechanics of glacial movement. Because ice, unlike water, is a solid. It does not simply pour downhill like a liquid. The way it moves is more nuanced, more layered, and in some respects more surprising than you might expect. Scientists understand glacial movement as arising from two distinct processes, working together in different proportions depending on the glacier, the terrain, and the temperature. The first of these is called basal sliding. This is exactly what it sounds like, the glacier sliding along its base, across the bedrock or sediment beneath it. For basal sliding to occur, there needs to be a thin layer of water at the interface between the ice and the rock below. This water acts as a lubricant, reducing friction and allowing the glacier to slip forward more freely. The water comes from several sources: pressure melting, where the sheer weight of the ice above lowers the melting point of ice at the base, geothermal heat rising slowly from the earth below, and meltwater filtering down through cracks from the surface. Where this basal layer of water is present and well developed, a glacier can slide with relative ease. The ice above rides forward on a film of meltwater so thin it would be nearly invisible to the eye, and yet its effect on the glacier's movement is profound. But not all glaciers slide easily at their base. In colder conditions, particularly in polar regions where temperatures are low enough that even the base of the glacier remains frozen, basal sliding contributes very little to the overall movement. In these cases, the glacier relies much more heavily on the second process: internal deformation. This is where the science becomes genuinely remarkable. Under sufficient pressure, ice does not simply sit still and remain rigid. It deforms. Slowly, continuously, almost imperceptibly, the ice crystals inside a glacier rearrange themselves, shift against one another, and allow the body of the glacier to change shape over time. The glacier, in effect, flows from within, not because it is melting, but because the ice itself is behaving, Under these conditions, almost like a very thick and extraordinarily slow fluid. Think of the way honey moves when you tilt a jar, not quickly, not dramatically, but with a kind of inevitable, patient spreading. Internal deformation in glacier ice is something like that, slowed by an almost incomprehensible factor, playing out not over seconds but across years. The primary mechanism of internal deformation is a process called creep. Creep is a term used across materials science to describe what happens when a solid material is subjected to sustained stress over a long period of time. The material does not break. It does not suddenly give way. Instead, it slowly, continuously changes shape, deforming in tiny increments, at the level of individual crystals and crystal boundaries, until the cumulative effect becomes measurable and meaningful. In glacier ice, creep occurs because the ice crystals are not rigidly locked in place. Under pressure, they can shift along specific internal planes within each crystal, planes defined by the molecular structure of ice itself. As individual crystals deform in this way, and as the boundaries between adjacent crystals allow for a degree of sliding and adjustment, the entire mass of ice gradually flows in the direction of the prevailing stress. It is a process that is entirely invisible from the outside. You cannot watch creep happening in real time. But given years, given decades, the cumulative effect of all those tiny adjustments is a glacier that has moved, sometimes hundreds of meters, sometimes kilometers, from where it began. The rate of creep in glacier ice is not constant throughout the glacier's body. It depends strongly on temperature. Warmer ice, ice closer to its melting point, deforms more readily than colder ice. This is why glaciers in temperate mountain ranges, where ice temperatures are relatively warm, often move faster than glaciers in the coldest polar environments. The same pressure acts on the ice in both cases, but the warmer ice yields more willingly to that pressure. Alongside creep, glacier ice can also deform through a second internal mechanism, faulting. Where creep is gradual and distributed throughout the ice, faulting is more localized. Under certain conditions of stress, ice can fracture along distinct planes, allowing one body of ice to move relative to another in a more abrupt, discontinuous way. Faulting in glaciers can produce visible structures in the ice, shear planes and bands where the movement has been concentrated, and in the debris-rich layers near a glacier's base, these shear zones can drag sediment and rock fragments upward into the body of the ice, creating those distinctive dark bands that sometimes appear near a glacier's margin. The interaction between creep and faulting, between slow distributed flow and more localized fracture, gives glacier ice its complex internal structure. These are not competing processes so much as complementary ones, each operating at different scales and under different conditions, together producing the full range of deformation that allows a glacier to move as a coherent body across the landscape. Now, one of the most striking things about glacial deformation is that it does not operate uniformly from top to bottom within the ice. The lower portions of a glacier, buried under the weight of everything above, experience the highest pressures, and it is here that the ice behaves most plastically. Plastic behavior, in the scientific sense, means that the material deforms continuously and permanently when stress is applied, without fracturing. Deep glacial ice under high confining pressure deforms in this plastic way, flowing and yielding and creeping with a kind of quiet compliance. The upper portions of the glacier are a different matter entirely. Near the surface, the confining pressure is lower. The ice is closer to the atmosphere, more exposed to temperature fluctuations, and not yet subjected to the immense weight that transforms the deeper layers. In this upper zone, the ice behaves in a more brittle fashion. Rather than deforming plastically under stress, it tends to crack. This is why the surfaces of glaciers are so often fractured and irregular. The great crevasses that open across a glacier's upper surface, those dramatic, sometimes terrifying chasms that can drop tens of meters into the ice, form because the brittle upper layer cannot deform fluidly to accommodate the movement happening in the more plastic ice below. As the deeper ice flows and shifts, the surface ice fractures under the resulting tension, splitting open in patterns that map the stresses moving through the glacier's body. The boundary between these two behavioral zones, between the brittle upper ice and the plastic lower ice, is not a sharp line. It is a gradual transition, influenced by temperature, pressure, crystal size, and the local speed of movement. But as a general principle, it holds throughout most of the world's glaciers, brittle near the top, plastic near the bottom, with all of the glacier's internal complexity arising from the interplay between these two regimes. There is something almost meditative about contemplating glacial movement in this way. Here is a material, ice, that most of us experience as rigid and unyielding, something that cracks when you strike it and shatters when it falls. And yet, given sufficient scale, sufficient pressure, and sufficient time, that same material flows. It deforms. It creeps slowly and continuously under forces that never relent. It moves with the patience of geology and the inevitability of gravity, reshaping itself and the land beneath it across timescales that dwarf anything in human experience. Every glacier on Earth is moving right now. Every one of them is responding to gravity, deforming under pressure, sliding at its base or flowing from within, carrying ice from the zones where it accumulates to the zones where it is ultimately lost. The movement is real, it is constant, and it has been happening, in some cases, for tens of thousands of years. You simply have to slow down enough to see it. And there is something in that, perhaps, worth holding on to. A reminder that the most significant transformations in the world are not always the ones that announce themselves loudly. Sometimes the most powerful forces are the ones that work quietly, persistently, and without any rush at all, changing everything, one imperceptible increment at a time. Ice, at the scale we encounter it in everyday life, seems like one of the simpler materials in the world. It is cold, hard, and transparent. It forms quickly and melts quickly. It fractures cleanly when struck. Most of us understand ice as something static, something that holds its shape until heat intervenes and returns it to water. That understanding is entirely reasonable for the ice in a glass or on a winter road. But inside a glacier, ice reveals a completely different set of behaviors. Behaviors that belong not to the world of everyday materials, but to the world of deep geology, to the slow, hidden physics of things that exist under pressures and timescales that no human hand could ever replicate. To understand how glacier ice truly moves, you have to go all the way down to the level of the crystal itself. We have already established that glacier ice deforms through a process called creep, a slow, continuous change of shape under sustained stress. But what actually happens inside the ice crystal when creep occurs? What is the mechanism, at the most fundamental level, that allows a rigid solid to flow? The answer lies in the internal architecture of each ice crystal, and in tiny structural imperfections that make all the difference. An ice crystal, like all crystals, is built from molecules arranged in a highly ordered, repeating pattern. In ice, water molecules organize themselves into a hexagonal lattice, a six-sided framework that gives snowflakes their characteristic symmetry and that gives glacial ice its internal structure. This lattice is not infinitely rigid. It has planes within it, specific orientations along which the molecular bonds are slightly weaker, along which layers of the crystal can slide relative to one another with less resistance. These are called basal planes. And the ability of one layer of an ice crystal to slide along its basal plane, slowly, under pressure, is one of the fundamental reasons that glacier ice can deform at all. When stress is applied to an ice crystal in the right orientation, the layers within it shift incrementally along these basal planes, allowing the crystal to change shape without fracturing. It is a form of movement that happens at the molecular scale, invisible to any eye, but cumulative across millions of crystals in a body of ice that may be hundreds of meters thick. But basal plane sliding alone does not fully account for glacial creep. There is another mechanism operating alongside it, one drawn from the broader science of materials, a concept called dislocations. A dislocation is a defect in the crystal lattice. Not a dramatic flaw, not a crack or a fracture, but a subtle irregularity in the arrangement of molecules, where the otherwise perfect repeating pattern of the lattice is interrupted or offset in a small way. These imperfections are present in virtually every real crystal, and in ice, they play a crucial role in deformation. When stress is applied to a crystal, dislocations do not simply stay where they are. They move. They propagate through the crystal lattice, shifting from one position to the next, threading their way through the molecular structure in response to the applied force. And as they move, they carry deformation with them, allowing the crystal to change shape incrementally, step by tiny step, as each dislocation passes through. This mechanism makes ice significantly easier to deform than a perfect, dislocation-free crystal would be. It is a counterintuitive idea that imperfections in a material's structure can actually make it more yielding, more capable of flow, but it is one of the foundational insights of materials science, and it applies directly to the ice inside a glacier. The movement of dislocations through the crystal lattice, combined with sliding along basal planes, gives glacier ice its capacity for slow, sustained deformation under the pressures it experiences deep within the glacial body. And alongside these mechanisms, there is one more process that shapes the internal behavior of the ice as it flows. Recrystallization. We encountered recrystallization earlier, in the context of how snow transforms into glacial ice in the first place. But recrystallization also occurs continuously within the ice as the glacier moves. As crystals deform under stress, as their lattices accumulate dislocations and their shapes become increasingly distorted, they eventually reach a point where reorganization becomes energetically favorable. New crystals nucleate and grow from the deformed material, replacing the strained, distorted crystals with fresh ones that are better oriented to accommodate the prevailing stress. This ongoing recrystallization means that glacier ice is not simply a static collection of crystals that formed once and then remained. The ice is continuously renewing its internal structure as it flows, old, deformed crystals breaking down and new ones forming in their place, the whole process driven by the thermodynamics of the ice under pressure. One of the most elegant outcomes of this continuous recrystallization, and of the sustained deformation that drives it, is a phenomenon called crystal preferred orientation. Over time, as a glacier flows in a consistent direction, the ice crystals within it do not remain randomly oriented. They gradually align. The basal planes of individual crystals, the planes along which deformation is easiest, tend to rotate toward orientations that are most favorable for accommodating the flow. The result is that the crystals throughout a body of flowing ice become progressively more aligned with one another, all oriented in roughly the same direction. This alignment has a direct mechanical consequence. Ice with a strong preferred crystal orientation, ice where the crystals are all lined up in the same general direction, deforms more easily than randomly oriented ice. The alignment creates a kind of structural cooperation among the crystals, allowing the entire mass to yield more readily to the stresses driving its flow. In the oldest, most deformed sections of a glacier, this crystal alignment can be remarkably strong. The ice there has been flowing for so long, under such sustained and directional stress, that its internal structure has been thoroughly reorganized around the direction of movement. In a sense, the ice has learned to flow, its own microstructure optimized, over centuries, for the task it has been performing. There is something beautiful about that idea. A material shaped by its own history of motion, carrying within its crystal structure a record of every increment of deformation it has undergone. Now, beyond the microscale, beyond crystals and dislocations and basal planes, the rate at which a glacier moves as a whole is governed by several factors that operate at a much larger scale. The thickness of the ice matters enormously. A thicker glacier exerts greater pressure on its base and on its own interior, driving faster deformation and, where water is present, more active basal sliding. A glacier that gains mass in its accumulation zone and grows thicker will, all else being equal, begin to flow more quickly in response. The steepness of the underlying terrain matters too. A glacier flowing down a steep slope is subject to greater gravitational stress than one moving across nearly flat ground. The force driving the ice forward is stronger, the deformation rate is higher, and the overall velocity increases. This is why glacier tongues that descend through steep mountain valleys often move faster than the broad, flat ice sheets of polar regions, where the driving stress is spread across an immense area. Temperature plays a role as well, perhaps the most direct role of all. Warmer ice, ice that is close to its melting point, deforms far more readily than cold ice. The molecular bonds in warm ice are less rigid, the dislocations move more freely, and the crystals yield more easily to applied stress. A glacier in a temperate mountain environment, where the ice throughout its body is relatively warm, will typically deform faster, and therefore flow faster, than a glacier of equivalent thickness in a much colder polar setting. These factors do not operate independently of one another. they interact. A glacier that is both thick and warm and flowing down a steep slope experiences all three influences simultaneously, and its movement reflects the combined effect of all of them. The equations that glaciologists use to model glacial flow must account for all of these variables at once, and the complexity of their interactions is part of what makes glaciology such a rich and demanding field. In many of the world's glaciers, the overall movement turns out to be remarkably evenly split between its two main sources. Roughly half of the motion comes from internal deformation, from all the creep and crystal sliding and dislocation movement we have been describing. And roughly half comes from basal sliding, from the glacier riding forward on that thin film of meltwater at its base. The exact proportion varies from glacier to glacier, and from place to place within a single glacier, but the broad equivalence between these two mechanisms is a striking feature of how many of the world's ice bodies actually behave. And now, with all of that in mind, with the internal mechanics of glacial flow established, we can turn to what happens when that flowing ice encounters the world above. Because all of this internal deformation, all of this slow and patient flow, eventually expresses itself at the surface of the glacier. And one of its most dramatic expressions is the formation of crevasses. A crevasse is a deep crack in the upper surface of the glacier, sometimes narrow, sometimes wide enough to swallow a person whole, sometimes extending tens of meters down into the ice before the darkness closes in. They are among the most visually striking features of any glacier, and also among the most dangerous, and their formation is a direct consequence of the contrast between the brittle upper ice and the plastic lower ice that we discussed in the previous chapter. As the deeper, more plastic ice flows and deforms, bending around the curves of the underlying terrain, accelerating over steep sections, spreading out across flatter ground, the brittle upper ice cannot match that movement perfectly. It cannot bend. It cannot flow. And so, under the tension created by the movement beneath it, it does the only thing brittle materials can do. It cracks. The pattern of crevasses on a glacier's surface is not random. It reflects, with remarkable precision, the stress field within the ice. Where the glacier is stretching, accelerating, spreading, flowing over a convex slope, tension crevasses open across the direction of stretching, wide and dramatic. Where the glacier is being compressed, slowing down, crowding together, being squeezed between valley walls, crevasses may close or be replaced by folding and thickening of the ice. At the edges of a glacier, where the ice moves more slowly due to friction with the valley walls, and the center moves more freely, crevasses form at characteristic angles, tilted patterns that map the shear stress between fast-moving and slow-moving ice. At the head of a glacier, where the ice begins its downward journey and pulls away from the stationary snowfield above, a particularly large crevasse called a bergschrund often forms, a deep, cold, frequently shadowed gap that marks the boundary between moving glacier and the static ice of the accumulation zone. Crevasses can open surprisingly quickly by geological standards, days to weeks in some cases, and they can also close again as the ice flows and the stress field changes. They are dynamic features, constantly forming, shifting, and healing as the glacier moves. They are also, in their way, a kind of window. A crevasse, if you can look down into one safely, reveals the interior of the glacier in cross-section. the layering of the ice, the color changes with depth, the transition from white bubbly surface ice to the deeper blue of denser, older material, all of it becomes visible in the walls of the crevasse, laid out like a geological diagram made real. And looking down into that cold blue depth, with the sound of meltwater somewhere far below and the immense silence of the glacier around you, it is easy to feel, just for a moment, the full scale of what a glacier actually is. Not a frozen surface, not a static feature of a landscape, but a deep, complex, moving body of ancient ice, full of structure and history and quiet, continuous motion. A world unto itself, hidden in plain sight. Every glacier carries within it a constant negotiation between two opposing tendencies. On one side, there is the capacity of ice to flow, to deform slowly, plastically, accommodating stress through creep and crystal sliding and the gradual reorganization of its internal structure. On the other side, there is the brittleness of ice when stress arrives faster than that slow flow can absorb it. Most of the time, in most parts of a glacier, these two tendencies exist in a kind of working balance. The ice deforms just quickly enough to relieve the stresses building within it, and the glacier moves as a coherent, continuous body. But not always. There are places within a glacier, and moments in its movement, where stress accumulates faster than creep can release it. Where the ice is being pulled apart, or pushed together, or forced to bend around a curve in the underlying terrain more quickly than its internal flow mechanisms can accommodate. In those places, the negotiation breaks down. The ice cannot yield smoothly. And when a material cannot yield smoothly under stress, it does something else entirely. It fractures. We have already talked about crevasses, those great open cracks in the glacier's upper surface, formed because the brittle upper ice cannot bend to match the flow of the more plastic ice below. But brittle deformation in a glacier is not limited to the surface. It operates throughout the upper portions of the ice, wherever the conditions for plastic flow are insufficient to relieve the stresses being applied. When ice cannot creep fast enough to accommodate the forces acting on it, faulting occurs. Not the dramatic, earthquake-generating faulting of deep crustal rocks, but a structurally similar process, fracture along a plane, with one body of ice displacing relative to another. These faults can be shallow tensional fractures, opening where the ice is being stretched beyond its capacity to flow. They can also form under compressive conditions, where the ice is being squeezed and the resulting shear stress exceeds what creep alone can handle. The conditions under which faulting occurs versus creep are governed largely by the rate at which stress is applied. Given enough time, ice is remarkably deformable. It will creep and yield to almost any sustained stress, given centuries in which to do so. But apply that same stress quickly, and the ice behaves as the brittle solid it appears to be at everyday scales. Strike a block of glacial ice with a hammer and it shatters. Apply the same force slowly, over years, and the ice will flow around it. This rate dependence is one of the defining characteristics of glacial ice as a material, and it governs the entire spectrum of deformation structures you find within a glacier, from the smooth, flowing folds of the deep interior to the sharp, angular fractures of the upper brittle zone. Which brings us to something that happens deep within the glacier, where the ice is under high confining pressure and temperatures are close to the melting point, a world of structures that would not look out of place in a metamorphic rock formation. Internal folding. As glacier ice flows, the layers within it, those annual bands and debris-rich strata and planes of differing crystal orientation that we described earlier, do not simply remain flat and horizontal. They are subjected to the same stresses that drive the overall flow of the glacier, and under those stresses, they bend. They buckle. They fold back on themselves in structures that, if you could see them in cross-section, would look strikingly similar to the folded rock layers exposed in the walls of an ancient mountain range. Folding in glacier ice can occur in several ways. Where compression is even and sustained, where the ice is being gently squeezed from both sides as it flows into a narrowing valley, for instance, the layers may fold symmetrically, developing smooth, regular waveforms that preserve the original thickness of each layer throughout the fold. These are called gentle, open folds, and they are among the more common deformation structures in glacial ice. Where compression is uneven, where one side of the glacier is moving faster than the other, or where the ice is being squeezed against an obstruction in the underlying terrain, the folds become more complex. Layers that begin as gentle undulations can tighten progressively as deformation continues, becoming more and more compressed until the fold limbs are nearly parallel. In extreme cases, the layers can be folded so tightly that they appear almost vertical, or even overturned, with older ice lying on top of younger ice in a sequence that completely reverses the original depositional order. Creep itself, that slow, continuous crystal scale deformation, is one of the primary drivers of folding. As different parts of a glacier flow at different speeds, as the ice in the center of a valley moves faster than the ice at the edges, and as deeper ice deforms more readily than the stiffer ice above, the internal layers are subjected to differential movement that progressively bends and rotates them. Given enough time, and enough accumulated deformation, even initially flat layers can be transformed into complex, multiply-folded structures that record the entire kinematic history of the ice's movement. Where creep-driven folding reaches its limits, where the stress becomes too concentrated, or the deformation too rapid, for smooth folding to continue, faulting takes over. The fold limb that has been thinning under progressive compression may ultimately fracture along a shear plane, with one sheet of ice riding over another in a thrust-like structure. Alternatively, layers under tension may be pulled apart entirely, leaving gaps or discontinuities in what was once a continuous stratigraphic sequence. The interplay between folding and faulting in glacier ice produces an internal architecture of extraordinary complexity, one that glaciologists can read, with appropriate techniques, to reconstruct the history of stress and flow that the glacier has experienced over its lifetime. Every fold axis, every fault plane, every zone of intense crystal alignment is a record of forces and movements that may be centuries or millennia old. Now, the terrain over which a glacier flows has a direct influence on all of these internal structures. A glacier is not flowing across an idealized smooth surface. It is moving over real bedrock that has hills and valleys, steps and ridges, over deepened basins and sudden steep drops. Each of these features in the underlying landscape imposes its own pattern of stress on the ice moving above it. Where the terrain steepens, where the glacier encounters a step in the bedrock and the ice is suddenly free to accelerate downslope, the ice stretches. The upper layers are pulled apart as the ice below accelerates, and the result is not just surface crevasses but internal thinning of the entire ice column. The glacier becomes thinner and faster in these zones, its layers stretched and attenuated, the internal structures drawn out and extended in the direction of flow. This thinning is not gradual or gentle. In steep sections, particularly where the glacier flows over what is called an icefall, a zone of highly crevassed, rapidly moving ice analogous to a waterfall in a river, the stretching can be dramatic. The ice breaks into a chaotic jumble of blocks and seracs, the internal layering is thoroughly disrupted, and the normal rules of calm glacial flow are replaced by something closer to controlled chaos. Icefalls are among the most visually spectacular and structurally complex features of mountain glaciers, and they are a direct consequence of the glacier encountering terrain steep enough to overwhelm its capacity for orderly flow. Below the icefall, where the slope eases again and the glacier slows, the ice is compressed. The thinned, stretched ice of the icefall zone crowds together, thickening again, its disrupted internal structure being reworked by the new compressive stress field. Layers that were stretched thin above may fold and thicken below. Fractures that open in the tensional zone may close as the ice compresses. The glacier reorganizes itself, progressively, as it adapts to each new section of terrain. All of this internal deformation, folding, faulting, stretching, compressing, creeping, recrystallizing, is the glacier's response to its landscape. It is the way the ice negotiates the world it moves through, accommodating each irregularity of terrain, each variation in slope and width and underlying geology, with whatever combination of plastic flow and brittle fracture the conditions demand. And through all of it, one other process is quietly at work. One that seems, at first, entirely unrelated to the mechanical story of ice deformation, but that turns out to be intimately connected to every aspect of how a glacier moves, how it erodes, how it responds to climate, and ultimately how it is lost. Water. Water is everywhere in a glacier. Not just at the surface, where meltwater pools and streams are visible to any observer, but inside the glacier and beneath it, threading through the ice in pathways both vast and microscopic, connecting the surface to the bed to the margins to the rivers and oceans beyond. Understanding water in a glacier means recognizing that it exists at three distinct levels, each with its own character and its own role in the glacier's life. The first is the supraglacial system, water on the surface of the glacier. In summer, or in any period of warming, the glacier's surface melts. Streams form on the ice, flowing across it in channels that can look remarkably like ordinary rivers, with meanders, with pools, with the same fluid dynamics you would find in any surface watercourse. These supraglacial streams can be strikingly blue against the white of the ice, and they can carry significant volumes of water across the glacier's surface before reaching an exit point. That exit point is often dramatic. Supraglacial meltwater does not always reach the glacier's edge by flowing across the surface. Frequently, it finds a faster route, downward, through the ice itself. Where crevasses open, meltwater pours in. Where the ice contains vertical shafts called moulins, cylindrical holes bored into the ice by the rotational force of a surface stream, the water plunges straight down, sometimes tens or hundreds of meters, carrying with it both the water and a significant amount of thermal energy that will influence conditions deep within the glacier. The transition from superglacial to unglacial, from water on the glacier to water within it, is one of the most consequential journeys in the glacial system. The unglacial system is the network of water pathways threading through the interior of the glacier itself. Water moves through this system in several ways, through crevasses and moulins, as we have described, through networks of smaller veins that form at the boundaries between ice crystals, where the melting point is slightly depressed by the impurities concentrated there, and through larger unglacial channels that form as water gradually melts its way through the ice, following pressure gradients toward lower elevations. The unglacial system is not well mapped in most glaciers. It is, by its nature, hidden, enclosed within hundreds of meters of ice, inaccessible to direct observation except in rare circumstances. But its existence is unmistakable. Water that enters the glacier at the surface must go somewhere, and the volumes involved, millions of liters per day on large glaciers during melt season, require pathways substantial enough to accommodate them. As water moves through the unglacial system, it does not simply pass through passively. It melts the ice around it. The thermal energy it carries, combined with the heat generated by friction as it flows, gradually enlarges the channels it occupies. A passage that begins as a narrow crack or a thin vein can widen over time into a genuine tunnel through the ice, a conduit large enough, in some cases, for a person to enter. These unglacial conduits are dynamic features. They open during periods of high meltwater input and may close again, through creep of the surrounding ice, during quieter periods. They route water toward the glacier's base with varying efficiency depending on their geometry, and they connect the surface system to the deepest and most consequential part of the glacial water network: the subglacial system. Water that reaches the base of the glacier, whether through unglacial conduits, through moulins, or through pressure melting at the bed, enters a world of extraordinary mechanical importance. At the interface between the ice above and the bedrock below, water dramatically alters the behavior of the glacier. It reduces the friction between ice and rock. It lubricates the bed, enabling or enhancing basal sliding. It can pressurize within the subglacial system, lifting the ice slightly from its bed and allowing it to move far more freely than it otherwise would. The subglacial drainage system is not a single, simple channel. It can exist in several forms, ranging from a distributed system of thin water films and linked cavities spread across much of the glacier's bed, to a more concentrated system of discrete channels incised upward into the base of the ice, called Roethlisberger channels, or R channels, that carry water efficiently toward the glacier margin. The transition between these different drainage configurations has profound effects on glacier velocity. A distributed system, spread broadly across the bed, maintains high water pressure throughout and keeps basal friction low, allowing the glacier to slide quickly. A channelized system, concentrating flow into efficient conduits, drains water more rapidly, reducing the water pressure across the rest of the bed and slowing the glacier's sliding. Glaciers can switch between these drainage configurations in response to seasonal changes in meltwater input. In early spring, when meltwater first begins reaching the bed after winter, it encounters a poorly developed drainage system and pressurizes rapidly, sometimes causing a seasonal speed-up in glacier flow. As summer progresses and the drainage system develops into efficient channels, the pressure drops and the glacier may actually slow again, even as meltwater input continues. This seasonal cycle of drainage system development and collapse is one of the clearest demonstrations that water and ice are not separate systems within a glacier. They are deeply, continuously, and dynamically coupled, each shaping the behavior of the other in ways that play out across every timescale from hours to millennia. And so the glacier, which appeared from the outside to be simply a body of solid ice, reveals itself on closer examination to be something far more intricate. A system in constant internal motion, ice deforming, layers folding and faulting, crystals aligning and recrystallizing, and threaded throughout with water, moving from surface to interior to base, connecting the atmosphere above to the bedrock below, linking the glacier's response to climate at the surface with its behavior at the very foundation of its movement. Every drop of meltwater that forms on a warm afternoon in the mountains, and finds its way through a crack or a moulin into the body of the glacier, becomes part of this system. It joins a network that is ancient and complex and constantly evolving. And in doing so, it participates, in a small but real way, in the movement of the ice above it. Water and ice, together, doing what glaciers have always done. Moving, slowly and inevitably, downhill. There is a moment, on any glacier, when the surface world ends and something else begins. It might be the edge of a moulin, one of those smooth-walled vertical shafts bored into the ice by a surface stream that has found a downward path. You approach it carefully, look over the rim, and see the water disappearing into the blue-dark interior, the sound of it fading quickly as it drops beyond sight. Or it might be a crevasse, wide enough to look down into, where the walls of ice narrow from brilliant white at the surface to a deep, compressed blue far below, and where the cold air rising from the depths carries a faint sound of water moving somewhere in the darkness. In both cases, the feeling is similar. You are standing at a threshold. On one side is the familiar world of wind and light and weather. On the other is the interior of the glacier, a world that operates entirely by its own rules, on its own timescales, in its own quiet and perpetual darkness. We ended the last chapter at the surface of the glacial water system, at the streams and pools and meltwater channels that form on a glacier's exterior during periods of warming. Now it is time to follow the water inward, to trace its journey from the surface, through the ice, to the hidden world at the very base of the glacier, where ice meets rock and where some of the most consequential processes in glaciology take place. The moulin is perhaps the most dramatic entry point. A moulin forms when a surface meltwater stream, flowing across the glacier, encounters a weakness in the ice, a crack, a crevasse, a point where the ice has been fractured by the stresses of movement, and finds that it can flow downward rather than continuing across the surface. Once that downward path is established, the stream begins to enlarge it. The turbulence of the falling water, and the thermal energy it carries, melts the ice walls of the shaft as the water descends, gradually widening the passage into a smooth, rounded tube that can extend tens or even hundreds of meters into the glacier. Moulins can be surprisingly large. The water pouring into them can roar with the force of a significant river. and yet they are transient features. A moulin that is active and vigorous in one summer season may be closed by the creep of the surrounding ice by the following year, its passage pinched off as the glacier's internal flow redistributes the ice around it. New moulins form elsewhere, where new fractures intersect new surface streams, and the glacier's drainage network continuously reorganizes itself in response to these changes. Crevasses serve a similar function, though they tend to be less efficient as drainage pathways because their geometry, wide at the top, narrowing with depth, does not channel water as effectively as the more cylindrical form of a moulin. Nevertheless, a significant amount of surface meltwater enters glaciers through crevasses, particularly in areas of high crevasse density where the glacier surface is heavily fractured. Water seeping into crevasses can refreeze at depth if it encounters ice that is below the freezing point, releasing latent heat and warming the surrounding ice, a process that plays a role in the thermal evolution of cold glaciers over time. Once inside the glacier, the water enters what glaciologists call the englacial system, the network of pathways within the ice itself. The englacial system is one of the least understood components of a glacier, largely because it is so difficult to observe directly. Drilling through hundreds of meters of ice is technically demanding and expensive. Natural and glacial conduits are rarely accessible, and the indirect methods available for inferring the internal structure of a glacier's drainage, analysis of water emerging at the glacier's margin, interpretation of borehole pressure records, geophysical techniques, provide useful information but cannot give the kind of detailed picture that direct observation would. What is known is that in glacial water moves through a variety of pathway types, ranging enormously in scale. At the smallest scale, water exists as thin films along the boundaries between individual ice crystals. The molecular structure of ice means that the very interface between two crystals, the grain boundary, is never perfectly frozen, even at temperatures below zero. A quasi-liquid layer persists at these boundaries, and water can move through the glacier along this network of grain boundary films, albeit extremely slowly. This pathway is most significant in temperate glaciers, where ice temperatures are close to the melting point throughout, and it contributes to the more distributed aspects of englacial water movement. At larger scales, water moves through networks of small channels and fractures within the ice. These can form along pre-existing weaknesses, the same crevasses and fracture planes that allow brittle deformation of the ice, or they can be melted open by the water itself as it flows along pressure gradients through the glacier. As channels enlarge over time, they can develop into genuine ice-walled conduits, tubular passages through the glacier that carry significant volumes of water, carved not into rock as a river's channel is, but into the ice itself. Ice-walled conduits are among the more remarkable features of a glacier's interior. Their walls are formed entirely of compressed glacial ice, sometimes displaying the same deep blue color and large crystal structure found in the densest parts of the glacier. Water flowing through them has melted its way through solid ice, and continues to do so as it flows, enlarging the conduit in the direction of flow while the creep of the surrounding ice works continuously to close it again. The conduit exists in a dynamic equilibrium between these two opposing tendencies, the melting that opens it and the creep that closes it. The geometry and connectivity of these englacial conduits are not fixed. They respond to changes in the glacier, to shifts in the stress field as the ice moves, to changes in meltwater input as climate varies, to the gradual evolution of the glacier's overall form. A conduit network that efficiently routes water through the glacier in one configuration may be disrupted or reorganized as the glacier thickens or thins, as it advances or retreats, as the pattern of crevassing on its surface changes and new input points emerge. This dynamic responsiveness is one of the defining characteristics of the inglacial system. It is not a stable, permanent drainage network like the river system carved into bedrock over geological time. It is a constantly evolving, self-organizing network that is always adjusting to current conditions, always finding new pathways as old ones close, always reorganizing in response to the glacier's own internal changes. Before the water reaches the base of the glacier, it may be temporarily held within the glacier's firn layer, that intermediate material between fresh snow and true glacial ice that forms in the accumulation zone. Firn is porous. Its interconnected air spaces allow water to percolate through it in the same way that water moves through a sponge or through sandy soil. During melt events, water produced at the surface can infiltrate the firn layer and be stored within it, held temporarily in the pore spaces before it gradually drains downward or refreezes. This storage capacity gives the firn layer a buffering function in the glacier's water system. It smooths out the sudden pulses of meltwater produced by rain events or rapid temperature changes, releasing water more gradually than if it simply flowed directly into the inglacial system without any intermediate storage. In the accumulation zone, where the firn layer is thick and well developed, this buffering effect can be substantial. A large rain-on-snow event that might otherwise send a sudden flood of water into the glacier's interior is instead partially absorbed by the firn, with the water stored and released over a period of hours or days. The inglacial and subglacial systems downstream receive a more gradual input, and the glacier's velocity response to the melt event is dampened accordingly. In the ablation zone, the lower part of the glacier where annual melting exceeds snowfall, the situation is different. Here, the firn layer is typically thin or absent. The surface consists of bare glacial ice, with no significant porous layer to absorb and buffer meltwater. Water produced on this surface enters the glacier more directly, through crevasses and moulins, with less opportunity for storage and smoothing. The inglacial system in the ablation zone receives sharper, more immediate pulses of meltwater in response to surface conditions, and the subglacial system below it experiences more rapid and variable water inputs as a result. This contrast between the buffered hydrology of the accumulation zone and the more direct hydrology of the ablation zone is one of the reasons why different parts of the same glacier can behave quite differently in their responses to melt events. In temperate glaciers, those where the ice temperature throughout is close to the melting point, as opposed to cold polar glaciers where most of the ice remains well below zero, the internal water system is particularly diverse and complex. Water in a temperate glacier exists simultaneously in many forms across the full range of scales we have been describing. There are the thin films at grain boundaries, present throughout the glacier wherever the temperature is at or near the melting point. There are the small channels and veins threading through the ice at intermediate scales. There are the larger inglacial conduits carrying water in discrete streams through the glacier's interior. And there are the cavities, spaces within the ice where water has pooled in local depressions or hollows, sometimes connected to the broader drainage network, sometimes temporarily isolated from it. All of these coexist within the same glacier, forming a multi-scale drainage system of extraordinary complexity. And all of them are changing, slowly or rapidly, seasonally or over longer periods, in response to the glacier's own movement and to the inputs it receives from above. The geometry of the glacier itself plays a role in shaping this internal water system in ways that can be counterintuitive. As the glacier moves, as it flows around bends, accelerates over steep sections, thickens in areas of compression and thins where the ice is being stretched, the stress field within the ice changes. These changes in stress affect the englacial conduit network, opening new fractures and closing old ones, redirecting water along new paths. A glacier that is thinning rapidly, for instance, may find that its englacial drainage network is being disrupted as the ice column shortens, potentially forcing water into new configurations. A glacier that is thickening may find old conduits being closed by the increased overburden pressure. The internal water system and the ice dynamics of the glacier are not independent of each other. They are coupled, each continuously influencing the other, in a feedback relationship that plays out across every timescale of glacial behavior. And now, following the water to its ultimate destination within the glacier, we arrive at the place where the most immediate and dramatic effects of glacial hydrology are felt. The base of the glacier. The subglacial environment is one of the more extraordinary places on Earth, not in any romantic or visible sense, since it is entirely inaccessible under hundreds of meters of ice, but in terms of the processes that occur there and the consequences they have for the glacier above. At the interface between the base of the ice and the bedrock or sediment below, several things are happening simultaneously. The weight of the glacier above generates immense pressure at the bed, pressure that varies from place to place depending on the ice thickness and the local geometry of the subglacial topography. This pressure has a direct effect on the melting point of ice. The higher the pressure, the lower the temperature at which ice melts. At the base of a thick glacier, the melting point can be depressed by a fraction of a degree relative to the melting point at the surface, enough that ice which would be stable at the surface is at or very close to its melting point at the bed. And there is another source of heat at the glacier's base. As the glacier slides across its bed, as the ice moves forward over rock and sediment, driven by gravity and by the internal flow we have described in such detail, friction is generated at the interface. The rubbing of ice against rock, and the deformation of sediment beneath the ice, both generate frictional heat. This heat is deposited directly at the glacier's base, where it contributes to the melting of ice at the bed. Even very small amounts of basal melting have significant consequences. The water produced at the glacier's base reduces the friction between ice and rock, lubricating the interface and allowing the glacier to slide more freely. This is the mechanism of basal sliding that we introduced in the previous chapter, the glacier riding forward on a thin film of meltwater at its base, the water produced by the very friction that its sliding generates. There is something elegantly self-sustaining about this process. The glacier slides, generating friction, which generates heat, which melts ice at the base, which produces water, which lubricates the bed, which allows more sliding, which generates more friction. The system feeds itself, within limits, as long as the glacier continues to move and as long as the thermal balance at the base remains favorable for melting. The distribution of this basal meltwater, how it spreads across the bed, how it is routed toward the glacier's margin, how its pressure varies from place to place, determines, to a very significant degree, how fast the glacier moves. Where basal water pressure is high, the ice is effectively lifted slightly from the bed, reducing the normal force at the interface and dramatically lowering friction. Where basal water pressure is lower, where the drainage system has organized itself into efficient channels that carry water away quickly, friction is higher and the glacier moves more slowly. This relationship between basal water pressure and glacier velocity is one of the most important and actively studied topics in glaciology. It connects the glacier's surface hydrology, the rain events, the melt seasons, the superglacial streams, directly to the glacier's dynamic behavior, through the inglacial pathways that route surface water to the bed. Changes at the surface, in other words, can translate rapidly into changes in how fast the glacier moves. A heavy rain event on a glacier's surface can send a pulse of water through the inglacial system to the bed within hours. That pulse temporarily raises basal water pressure, reducing friction, and causes the glacier to accelerate. Instruments measuring glacier velocity can detect this acceleration in real time, a speed-up that may last hours to days before the drainage system adjusts and the pressure drops again. This responsiveness of glacier dynamics to hydrological inputs is not merely an academic curiosity. In a warming climate, as melt seasons lengthen and intensify, and as rain events become more frequent on surfaces that were previously too cold for rainfall, the delivery of water to glacier beds is increasing. The implications for glacier velocity, and for the rate at which ice is transported toward the ocean, are a central concern in current projections of sea level change. All of this, from the moulin on the surface to the thin film of meltwater at the bed, is part of a single connected system. Water falls as snow, accumulates over decades into glacial ice, melts at the surface in summer, enters the glacier through fractures and shafts, moves through the inglacial network, reaches the bed, lubricates the sliding of ice across rock, and eventually emerges at the glacier's margin, in meltwater streams, in subglacial outflows, in the turbid rivers that carry the flour of ground rock from beneath the ice into the valleys and ultimately to the sea. Every component of this journey is connected to every other. The fairnet buffers the surface input. The crevasses and moulins that provide entry points. The inglacial conduits that route water downward. The subglacial drainage system that distributes it at the bed. The frictional heat that produces it in the first place. A glacier, seen this way, is not just ice. It is a hydrological system of great complexity, in which water and ice are partners, each shaping the behavior of the other, across every scale from the molecular to the continental. And in the cold and the dark at the glacier's base, where no light has ever penetrated and where the pressure is immense and the temperature is barely at the threshold of melting, that partnership is at its most intimate. Ice above, rock below, and between them, the thin, consequential film of water that makes all the difference. Beneath every glacier, the ground is not entirely still. Far below the ice, heat is rising. Not the heat of the sun, which the glacier's surface reflects and absorbs in different measures through the seasons, and not the frictional heat generated by the glacier's own sliding, but an older, deeper heat. The heat of the Earth itself, moving upward through kilometers of rock from the planet's interior, arriving at the base of the glacier in quantities that vary from place to place depending on the local geology, but that are present, always, beneath every glacier on Earth. This is geothermal heat. And while its contribution to basal melting is modest compared to frictional heat in fast-moving glaciers, it is continuous and inescapable. It never ceases. Through winter and summer, through periods of high melt and periods of cold, the geothermal flux arrives at the glacier's base at its own steady pace, contributing a small but real amount of energy to the thermal budget of the basal environment. In some places, geothermal heat is anything but modest. Where glaciers overlie regions of volcanic activity, in Iceland, in parts of Antarctica, beneath certain sections of the Greenland ice sheet, geothermal flux can be dramatically elevated. Beneath Iceland's Vatnajökull ice cap, volcanic systems generate enough heat to melt substantial quantities of basal ice, feeding subglacial lakes and producing the occasional catastrophic glacial outburst flood known as a Jökulhlaup. These floods emerge from beneath the ice with extraordinary force, carrying water, sediment, and ice blocks across the landscape in events that can reshape entire river valleys within days. But even in geologically quiet regions, far from any volcanic system, underlain by ancient, cold, stable rock, the geothermal heat flux contributes to the thermal state of the glacier's base, and in thick, slow-moving polar ice sheets, it may be the dominant source of basal melting. Beneath the Antarctic ice sheet, in regions where the ice is 3 or 4 kilometers thick and has been accumulating for millions of years, geothermal heat has melted enough ice at the base to create subglacial lakes, bodies of liquid water trapped beneath kilometers of ice, isolated from the atmosphere, existing in complete darkness under pressures that would be crushing to anything familiar from the surface world. These subglacial lakes are among the most extreme environments on Earth, and they have become subjects of intense scientific interest, both for what they reveal about the thermal and hydrological state of the ice sheet above them, and for what they might tell us about the possibility of life in environments of comparable extremity elsewhere in the solar system. But we are getting ahead of ourselves. Let us return to the base of the glacier, and to the water that accumulates there. We established in the previous chapter that basal meltwater, produced by frictional heat, by pressure melting, and by geothermal flux, plays a decisive role in determining how fast the glacier slides. The mechanism, at its most fundamental, is straightforward. Water at the bed reduces friction between ice and rock. But the details of how this happens, and why the effect varies so dramatically from place to place and from season to season, depend on the structure of the subglacial drainage system, one of the most complex and consequential aspects of glacial hydrology. To understand that drainage system, it helps to think about what the base of a glacier actually looks like. Bedrock is not smooth. At every scale, from the kilometer-scale hills and valleys of the subglacial topography down to the millimeter-scale roughness of individual rock surfaces, the bed of a glacier is irregular. It has bumps and hollows, ridges and depressions, facets and channels carved by previous glaciations or by the chemical weathering of the rock itself. The ice above it conforms to this surface imperfectly, particularly where the ice is moving quickly and cannot adjust its shape fast enough to maintain perfect contact with every irregularity below. Where the ice fails to maintain contact with the bed, where it bridges across a hollow in the rock surface, or where water pressure has pushed it slightly upward, a cavity forms. A subglacial cavity is a void at the glacier's base, a space between the ice above and the rock below, typically filled with water, enclosed on all sides by either ice or rock. Cavities form preferentially on the downstream side of bedrock bumps, the lee side, where the ice, having ridden over the top of the bump, loses contact with the rock as it descends the other side. They can range from tiny pockets a few centimeters across to large, interconnected voids extending for meters or tens of meters. In regions of rough bedrock and active basal sliding, the subglacial cavity network can be extensive, covering a significant fraction of the glacier's total bed area. Water fills these cavities and connects them, moving from one to the next through narrow passages, through the thin films between ice and rock, through pores in the rock surface itself. This network of linked cavities, films, and pores constitutes what glaciologists call the distributed drainage system, distributed because the water is spread broadly across the glacier's bed rather than concentrated into discrete channels. The distributed system is the natural resting state of subglacial drainage in many glaciers, particularly at the beginning of the melt season, before the water inputs from the surface have been sufficient to develop more organized drainage. It drains water slowly. The pathways are tortuous. Water must thread its way through a labyrinth of cavities and connections, following pressure gradients that may route it through many indirect paths before it reaches the glacier's margin. The residence time of water in a distributed system is long, and the system can accommodate only limited water flux before the pressure throughout it rises significantly. This tendency toward high pressure is the key to understanding the distributed system's effect on glacier velocity. When water pressure in the subglacial cavity network is high, when the cavities and connections are filled and pressurized, the effective normal stress between the ice and the bed is reduced. The weight of the ice above is partially supported by the pressurized water rather than by direct contact between ice and rock. Friction decreases. The glacier slides faster. The relationship between basal water pressure and glacier sliding speed is not linear. At low to moderate water pressures, increasing the pressure causes a gradual increase in sliding speed. But as the water pressure approaches the overburden pressure, as it approaches the weight of the ice column above, the effect becomes dramatically stronger. Near flotation pressure, very small increases in basal water pressure can produce very large increases in sliding velocity. The glacier, in effect, is nearly floating on its bed, and the slightest additional lubrication allows it to surge forward. This strong sensitivity of sliding speed to basal water pressure is why glaciers respond so rapidly to hydrological inputs. A pulse of meltwater arriving at the bed, from a rain event, from a period of intense surface melting, from the sudden drainage of a superglacial lake through a moulin, can pressurize the distributed system quickly, because the system's capacity to drain water is limited. The pressure rises, the ice lifts slightly from the bed, friction drops, and the glacier accelerates. The speed up can be measured in hours. What happens next depends on how the drainage system evolves in response to the increased water input. If the input remains modest and the distributed system can accommodate it without developing into a more organized configuration, the pressure eventually equilibrates and the glacier settles back toward its previous speed. But if the water input is large enough and sustained enough, the distributed system may begin to transition toward a channelized configuration. As water pressure in the distributed system remains high and water continues to flow through the cavity network, some of the connections between cavities begin to enlarge. Water flowing through a narrow passage melts the ice above it, gradually widening the passage into a more open channel. As the channel enlarges, it becomes more efficient. It can carry more water at lower pressure. Water from the surrounding distributed system is drawn toward these more efficient drainage pathways, and the channels grow at the expense of the distributed network around them. The result is a progressive reorganization of the subglacial drainage, from a broad, distributed network of linked cavities toward a more concentrated system of discrete channels that drain the bed efficiently, drawing water pressure down across much of the glacier's base as they do so. This channelized system, with its lower water pressures and more effective drainage, actually reduces basal sliding speed relative to the highly pressurized distributed system it replaced. The glacier may slow during the height of summer, even as melt rates at the surface are at their maximum, because the well-developed channel network is efficiently removing water from the bed rather than allowing it to pressurize. This seasonal cycle, from poorly drained, high-pressure distributed system in spring to well-drained, lower-pressure channelized system in midsummer, and back again as winter shuts down the water inputs and the channels close through creep, is one of the defining rhythms of glacier hydrology. It drives a corresponding cycle in glacier velocity that has been measured on glaciers around the world, and it represents one of the clearest examples of the tight coupling between a glacier's hydrological state and its dynamic behavior. Beneath the ice, alongside the cavity network and the channels incised into the base of the ice, there is another component of the subglacial drainage system that deserves its own attention: the sediment. Many glaciers do not flow directly over hard bedrock. They flow over a layer of sediment, till, in glaciological terminology, that has been produced by the glacier's own erosion of the underlying rock and deposited beneath the ice. This subglacial till can range from a thin drape of fine-grained material to a thick, saturated layer tens of meters deep, and its presence fundamentally changes the character of the subglacial environment. Till is porous. It contains spaces between its grains, pore spaces, that can be filled with water. When subglacial meltwater is present, it does not only occupy the cavities and channels at the ice-rock interface. It also infiltrates the till, saturating it and pressurizing the water within its pore spaces. Water held in the pores of subglacial sediment is part of the subglacial drainage system, but it moves far more slowly than water in cavities or channels. It seeps through the till under pressure gradients, finding its way through the interconnected pore network at rates controlled by the permeability of the sediment. Fine-grained till, rich in clay and silt, has very low permeability and holds water under high pressure for extended periods. Coarser till, sandy or gravelly, drains more readily. The poor water pressure in subglacial till has consequences not just for drainage but for the mechanical behavior of the till itself. When poor water pressure is high, when the water in the sediment pores is pressurized close to the overburden pressure of the ice above, the effective strength of the till is reduced. The grains are partially supported by the pressurized water rather than by grain-to-grain contact, and the till behaves more like a viscous fluid than a solid. Under these conditions, the till can deform, it can flow slowly, in response to the shear stress applied to it by the moving ice above. This deformation of subglacial till is another mechanism by which glaciers move. Where the till is soft and saturated, the glacier does not slide over it so much as ride within it, the upper layers of till being sheared and deformed by the ice above, contributing to the forward motion of the glacier without requiring sliding at the ice-rock interface at all. The relative importance of sliding, till deformation, and internal ice deformation in producing a glacier's overall motion varies from glacier to glacier and from place to place within a single glacier, depending on the nature of the bed, the availability of water, and the thermal state of the ice. Some glaciers move almost entirely by internal deformation, with little basal contribution. Others move almost entirely by basal processes, with the internal deformation contributing only a small fraction. Most fall somewhere between these extremes, with all three mechanisms contributing in proportions that shift with changing conditions. What ties all of these mechanisms together? What connects the slow creep of ice crystals deep within the glacier to the sliding of the base and the deformation of the till, is water. Water in its many subglacial forms, in the thin films between ice and rock, in the cavity network, in the channel systems, in the pore spaces of the sediment. Water produced by the glacier's own motion, by geothermal heat, by the infiltration of surface meltwater through the englacial system. Water that is always seeking a lower pressure, always moving toward the glacier's margin, always reorganizing the drainage network it flows through as it goes. The subglacial drainage system, in all its complexity, its linked cavities and its efficient channels, its permeable sediment layers and its pressurized pore spaces, its slow distributed flow and its rapid channelized drainage, is the hidden circulatory system of the glacier. It connects the atmosphere above to the bedrock below. It translates changes in surface climate into changes in glacier dynamics with a speed and directness that continues to surprise scientists who study it. And it operates in complete darkness, under pressures that would be incomprehensible at the surface, in a cold and water-saturated world that no human eye has ever directly seen. In many ways, the base of a glacier is the least known and most consequential part of the entire system. It is where the glacier's history of motion is ultimately decided, where the balance between friction and lubrication, between ice and water and rock, determines how fast the ice moves and how quickly it delivers its mass to the sea. It is where geothermal heat from the deep earth meets the accumulated snowfall of centuries above. It is where water, moving slowly through a labyrinth of cavities and pores and channels, exerts an influence on the glacier's behavior far out of proportion to the thin layer it occupies. Everything that happens at the glacier's surface, every snowflake that falls, every summer's melting, every rain event that sends water plunging through a moulin, eventually makes itself felt at this hidden interface. And in the cold silence far beneath the ice, the glacier responds. The story of water beneath a glacier does not follow the rules we are accustomed to. On the surface of the Earth, water obeys a simple and familiar principle. It flows downhill. Gravity pulls it toward lower elevations, and it follows that pull with complete reliability, from mountain to valley, from valley to river, from river to sea. We depend on this predictability so thoroughly that we rarely pause to question it. Of course, water flows downhill. What else would it do? Beneath a glacier, the answer to that question becomes considerably more complicated. To understand why, we need to first understand how the subglacial drainage system that we explored in the previous chapter continues to evolve over the course of a melt season, and what happens when the conditions that sustain one type of drainage give way to conditions that favor another. We left the subglacial system in a state of transition, the distributed network of linked cavities, which develops first as meltwater begins reaching the bed in early spring, gradually giving way to a more organized, channelized drainage as water inputs increase through the season. That transition does not happen all at once, and it does not happen uniformly across the entire glacier bed. It proceeds incrementally, as individual channels enlarge and capture drainage from the distributed system around them, progressively reorganizing the flow of water at the bed into a more concentrated and efficient configuration. The key difference between these two drainage states lies in their efficiency, their capacity to move water through the system without allowing pressure to build. A distributed system is inherently inefficient. Water moves through it slowly, threading through a labyrinth of cavities and thin films and pore spaces, encountering resistance at every turn. When meltwater inputs are low, as they are in early spring, or during a cold period in midsummer, the distributed system can accommodate the flux without excessive pressurization. But when inputs increase, the system fills faster than it can drain, and pressure rises throughout the network. High pressure in the distributed system, as we have established, reduces basal friction and accelerates the glacier. This is why glaciers often show their fastest velocities in spring, when the first significant meltwater reaches a bed that has spent the winter with a poorly developed, low-capacity drainage system. The bed is unprepared for the sudden influx, the pressure spikes, and the glacier surges forward. As summer progresses and channelized drainage develops, the efficiency of the system increases markedly. Channels can carry far more water than the distributed network for a given pressure gradient, and they tend to draw water toward themselves, their lower pressure acting as a sink that captures drainage from the surrounding distributed system. As more and more of the bed's drainage is captured by channels, the pressure throughout the system drops. The distributed network deflates, in a sense. The cavities drain partially, the pore spaces in the till lose some of their pressurization, and the effective friction between ice and bed increases again. The glacier slows. This counterintuitive slowing during peak melt season, when meltwater production at the surface is at its highest, has been observed on glaciers around the world and is one of the more elegant demonstrations of how the efficiency of the drainage system, rather than the absolute volume of water available, controls the glacier's dynamic response to hydrology. The channelized system that replaces the distributed system is not permanent. As autumn arrives and surface melting decreases, the water inputs that sustain the channels diminish. Without sufficient flow to maintain them against the creep of the surrounding ice, the channels begin to close. The ice deforms inward, narrowing the conduits, reducing their capacity. By the time winter is fully established and surface meltwater has ceased, the channel network has largely collapsed, leaving behind a distributed system of residual cavities and water films that will serve as the starting point for the following year's cycle. This annual rhythm, distributed system in winter and early spring, channelized system through summer, back to distributed in autumn, is one of the fundamental periodicities of glacial hydrology. It connects the glacier's dynamics to the climate in a direct and measurable way, and it means that a glacier's behavior in any given season reflects not just the current conditions but the history of hydrological development that has preceded them. Now, within this cycling drainage system, there are places beneath some glaciers where water does not simply pass through on its way to the margin. There are places where it accumulates. Subglacial lakes. The existence of large bodies of liquid water beneath glaciers, beneath kilometers of ice, in the cold and the dark, is one of the more remarkable discoveries in modern glaciology. The largest and most studied of these are found beneath the Antarctic ice sheet, where the combination of geothermal heat from below and the insulating effect of the overlying ice creates conditions in which liquid water can persist indefinitely. Lake Vostok, the largest known subglacial lake on Earth, lies beneath nearly 4 kilometers of Antarctic ice. It covers an area roughly the size of Lake Ontario, one of the North American Great Lakes. It has been isolated from the atmosphere for somewhere between 15 and 25 million years. The water within it has not seen sunlight in geological epochs. And yet it is liquid, maintained in that state by geothermal heat from below and by the pressure-induced depression of the melting point that we discussed in the context of basal melting more broadly. Lake Vostok is not alone. More than 400 subglacial lakes have been identified beneath the Antarctic ice sheet, ranging from small, localized bodies of water to large, deep lakes that rival significant surface water bodies in their dimensions. They are identified primarily through radar surveys conducted from aircraft. The radar signal penetrates the ice and reflects differently from water than from ice or rock, allowing the extent of subglacial lakes to be mapped even through kilometers of overlying glacier. Some of these lakes are isolated, their water held in place by local topographic basins for millions of years. But others are connected. Water can move between subglacial lakes through the drainage network at the ice sheet's base, and this movement is not always slow or gradual. Observations made through repeated satellite measurements of the ice sheet surface have revealed something striking. The ice surface above some subglacial lakes rises and falls over periods of months to years, in patterns that indicate the lakes themselves are filling and draining. Water is moving between them, through subglacial pathways, in volumes large enough to change the thickness of the ice above by meters. These subglacial lake drainage events, sometimes called active subglacial hydrology, to distinguish them from the more static picture of isolated, long-stable lakes, represent a form of hydrological activity at the base of the ice sheet that was not anticipated before satellite monitoring of ice surface elevation became routine. They suggest that the subglacial drainage network beneath ice sheets is far more dynamic than previously understood, capable of routing large volumes of water across long distances in relatively short periods. The movement of water between connected subglacial lakes has consequences for the ice sheet above. When a lake drains, the loss of water pressure at the bed in that area allows the ice to settle closer to the rock, increasing basal friction and potentially slowing ice flow locally. When a lake fills downstream, the increase in water pressure there reduces friction and may accelerate flow. The net effect of these lake-to-lake transfers on the overall dynamics of the ice sheet is a subject of active research. But the movement of water between subglacial lakes also raises a deeper question, one that leads us to perhaps the most conceptually surprising aspect of subglacial hydrology. If water can move from one lake to another beneath the ice, and if some of that movement appears to go against the simple downhill direction that surface water always follows, then what is actually guiding the flow of water at the base of a glacier? The answer requires letting go of the intuition that gravity alone determines where water goes. At the base of a glacier, water does not flow simply downhill in the topographic sense. It does not simply move from higher bedrock elevations to lower ones, following the contours of the rock surface as a surface stream would. It moves according to something more complex, a quantity called hydraulic potential. Hydraulic potential is the total energy available to drive water flow at any given point. It includes the gravitational component, the elevation of the water, but it also includes the pressure component. And at the base of a glacier, pressure is not uniform. It varies from place to place depending on the thickness of the ice above, the local geometry of the bed, and the state of the drainage system. Where the ice is thicker, the overburden pressure is greater, and the pressure imposed on the basal water is higher. Where the ice is thinner, the pressure is lower. This pressure component of hydraulic potential can be enormous compared to the gravitational component. The weight of a kilometer of ice pressing down on basal water creates a pressure vastly greater than the pressure difference created by a few tens of meters of change in bedrock elevation. And water, responding to total hydraulic potential rather than gravity alone, will flow away from regions of high pressure, which are generally regions of thick ice, even if that means moving uphill in the topographic sense. Let that sit for a moment. Beneath a glacier, water can flow uphill. Not because of any exotic physical process, not because normal physics is suspended in the subglacial environment, but because the pressure gradient imposed by the varying thickness of the ice above is large enough to overwhelm the gravitational gradient that would otherwise dictate the direction of flow. Water moves from high hydraulic potential to low hydraulic potential, and high hydraulic potential at the glacier's bed is found where the ice is thickest, regardless of the elevation of the bed at that point. The practical implication of this is that subglacial water routing can be counterintuitive in the extreme. A river on the surface will always flow toward lower ground. But a subglacial drainage pathway may route water directly up a slope in the bedrock if the pressure gradient from the ice above is strong enough. It may divert water sideways, away from what appears to be the nearest topographic low, because the hydraulic potential gradient points in a different direction. It may carry water through a seemingly inefficient path that, when the ice thickness is properly accounted for, turns out to be the path of steepest potential descent. Glaciologists model subglacial water routing by calculating the hydraulic potential at every point on the glacier's bed, taking into account both the bedrock topography and the ice surface elevation, and identifying the pathways along which water would flow from high potential to low. These models reveal drainage networks beneath ice sheets that are often dramatically different from what the bedrock topography alone would suggest. Subglacial rivers flow up into bedrock basins and over ridges that would be impassable barriers to surface water. Drainage divides beneath the ice bear no relationship to the topographic divides visible on the surface. The direction and slope of the ice surface, determined by the accumulation pattern, the flow dynamics, and the mass balance of the glacier, influences subglacial water routing more strongly than the topography of the bed in many cases. A change in the ice surface slope, caused perhaps by a period of rapid thinning or thickening, can redirect subglacial drainage pathways across large areas, potentially rerouting water toward different parts of the glacier margin and changing the delivery of fresh water to the ocean at specific locations. This sensitivity of subglacial drainage to ice surface geometry means that as glaciers and ice sheets respond to climate change, thinning, retreating, changing their surface slopes, the routing of water at their beds will change as well. Pathways that currently carry meltwater in one direction may be redirected. Regions of the bed that currently receive significant lubrication may lose it. Others that are currently well drained may find themselves receiving increased water flux. The consequences of these rerouting events for glacier dynamics are difficult to predict precisely, because the feedbacks involved are complex and the subglacial environment is so poorly observed. But the principle is clear: the behavior of glaciers is sensitive not just to how much water is present at their beds, but to where that water goes, and where it goes is determined not by the simple downhill logic we apply to surface water, but by the more complex calculus of hydraulic potential in a pressure-dominated environment. Water, in the subglacial world, plays by different rules. It flows where the pressure gradient tells it to flow, not where gravity alone would send it. It fills lakes that have been sealed for millions of years. It moves between those lakes in pulses that lift and lower the ice sheet surface by meters. It travels uphill through bedrock passages that would stop any surface river. And in doing all of this, it shapes the behavior of the ice above it in ways that are still being discovered and mapped and understood. There's a kind of quiet strangeness to this that is worth dwelling on. We live in a world where water's behavior feels completely known to us. We have watched it fall and flow since childhood. We know intuitively that it seeks the lowest point, that it runs toward the sea, that it follows gravity with perfect obedience. And all of that is true, at the surface, where gravity is the dominant force governing its movement. But go deep enough, and add enough pressure, and the familiar rules give way to something richer. The water beneath a glacier is the same water that falls as snow on the surface, that flows in summer streams, that feeds the rivers we know. But in its subglacial journey, it enters a regime where pressure rewrites the rules of flow, where uphill is sometimes the natural direction, where the weight of kilometers of ice above is more consequential than the slope of the ground below. The glacier carries this hidden river within it, moving in directions that defy simple intuition, following gradients invisible to any surface observer, threading through a world of ice and rock and darkness that lies beneath the familiar, visible face of the glacier we can see and touch and stand upon. And somewhere in that hidden world, water that began as a snowflake is making its quiet, unhurried, pressure-guided way toward the sea. Water, moving beneath a glacier, does not travel in straight lines. We have established that subglacial water follows hydraulic potential rather than simple topographic slope, that it responds to pressure gradients driven by the weight of overlying ice as much as to the pull of gravity. But the actual pathways it carves through the subglacial environment are more intricate still, shaped by the detailed geometry of the bed, the varying thickness of the ice, and the way that efficient drainage tends to organize itself into branching networks rather than single corridors. Some subglacial channel networks are arborescent. The word comes from the Latin for tree, and it describes exactly what these drainage systems look like when mapped: a branching structure, with smaller tributaries joining larger ones, converging progressively toward a main outlet at the glacier's margin, much as the branches of a tree converge toward the trunk. In a surface river system, this branching pattern develops because small streams erode their own channels into the landscape over time, gradually organizing the drainage of a watershed into a hierarchical network. In a subglacial channel system, the same organizational principle applies, but driven by different mechanics. Subglacial channels grow where water flux is highest. As a channel enlarges through melting of the overlying ice, it captures drainage from the surrounding distributed system, increasing its flux further and enlarging still more rapidly. Smaller channels feeding into a larger one merge with it, their drainage absorbed, their own enlargement stalled as the larger channel draws the available water toward itself. Over the course of a melt season, this competition between channels can produce a well-organized, arborescent network that efficiently drains large areas of the glacier's bed through a relatively small number of major conduits. What makes subglacial arborescent networks particularly interesting is the direction in which their tributaries can flow. Because subglacial water routing follows hydraulic potential rather than bedrock topography, the tributaries of a subglacial channel system can flow uphill through the bedrock, ascending slopes that no surface stream could climb, if the pressure gradient imposed by the ice above drives them in that direction. Water at the interior of a thick glacier, under high overburden pressure, can be routed outward toward the margin along pathways that ascend through the bedrock geometry, converging on main channels at lower hydraulic potential even though the path involves local uphill movement. This means that the interior of the glacier, the region of thickest ice and highest basal pressure, can actively feed drainage outward toward the margin along arborescent pathways that branch back into the interior like roots reaching upward. Water from deep beneath the central, thickest part of the glacier can travel along these branching pathways to join the main drainage channels, contributing to the overall flux without ever having descended to the margin by the most direct topographic route. The shape of the bed itself exercises a constant influence on where water goes and what it does when it gets there. In many glaciated landscapes, the bed beneath the glacier is not simply a slope descending from the accumulation zone to the margin. It contains overdeepened basins, areas where the glacier has eroded the bedrock more deeply than the surrounding terrain, creating enclosed depressions in the subglacial topography that sit below the elevation of the glacier's margin. These overdeepenings are a characteristic product of glacial erosion, formed where the ice was particularly thick and active and the erosive power correspondingly intense. Water entering an over-deepened basin faces a challenge. To exit the basin and continue toward the glacier's margin, it must ascend the adverse slope on the downstream side, the up-valley wall of the depression. In a surface landscape, such a basin would simply fill with water until it overtopped its lowest rim and spilled out. Beneath a glacier, the situation is more complex. The hydraulic potential gradient may still drive water out of the basin and up the adverse slope, if the ice surface above slopes sufficiently toward the margin to create a strong enough pressure gradient. But where the adverse slope is steep relative to the ice surface gradient, the hydraulic potential may actually discourage water from taking the direct route through the deepest part of the basin. Instead, water may be routed around the flanks of the over-deepening, along the sides of the basin, where the bed is shallower and the hydraulic potential gradient more favorable, rather than through the basin's lowest point. This flank routing has been observed and modeled in glaciated valleys around the world. The drainage does not take the most topographically obvious path. It is diverted sideways, around obstacles that hydraulic potential renders more formidable than their topographic prominence alone would suggest, and routed along pathways at the glacier's margins that maintain a more favorable gradient toward the outlet. The underside of the glacier itself, the ice ceiling of the subglacial environment, is also shaped by these water movements in ways that are not immediately obvious. Where subglacial water flows at high velocity through channels, it carries thermal energy that melts the ice above it. The melt patterns on a glacier's underside can be complex and asymmetric, reflecting the channelized flow of water in some areas and the slower distributed flow in others. Where channels are well established and water flux is high, the ice ceiling may be melted upward into irregular, scalloped forms, surfaces shaped by the turbulence of the flowing water, marked by the same dissolution patterns you might see on the ceiling of a cave through which a river flows. Where the distributed system dominates and water moves slowly through cavities and films, the melt patterns are more subdued, a gentle, pervasive lowering of the ice surface rather than the focused erosion of the channelized zones. The result is an underside of the glacier that is topographically complex in its own right, shaped by the ongoing interaction between the moving water and the ice above it, changing continuously as the drainage system evolves through the season. All of this, the arborescent drainage, the flank routing around over-deepenings, the melt patterns on the ice ceiling, is part of the hidden machinery of the subglacial world. It is inaccessible, largely invisible, inferred from instruments and models and the occasional borehole that punches through hundreds of meters of ice to sample conditions at the bed. But now, alongside the water, something else is present at the base of the glacier. Something harder. Something older. Something that has been accumulating in the ice over centuries of movement and erosion, waiting to be carried wherever the glacier takes it. Rock. The relationship between a glacier and the rock beneath it is one of the oldest and most consequential in the physical geography of the Earth. It is not a passive relationship. The glacier does not simply slide over the bedrock as a harmless layer of ice moving across an unchanging surface. It grinds. It scrapes. It plucks. It erodes the rock with patient, relentless, extraordinary effectiveness, reshaping mountains, deepening valleys, excavating basins that will later fill with lakes, carving the landscapes that define some of the most beautiful terrain on Earth. And the agent of that erosion is not the ice alone. It is the ice together with the rock it carries within it. Rock enters a glacier in several ways. At the glacier's margins, cliffs and slopes above the ice are constantly being weathered by frost, water expanding as it freezes and rock fractures, gradually prizing fragments loose until they fall onto the glacier's surface below. These rock falls deliver debris to the glacier's surface, where it accumulates in stripes called lateral moraines, long lines of dark material along the edges of the glacier, marking where the valley walls have shed their material onto the ice. Where two glaciers merge, their lateral moraines merge with them, combining into a central stripe called a medial moraine that runs down the middle of the combined glacier, visible from above as a dark thread against the white of the ice. But not all of the rock in a glacier rides on its surface. Some of it is incorporated into the ice itself, frozen into the body of the glacier and carried along in its interior. And some of it, the material that does the most significant erosive work, is frozen into the glacier's base. Rocks and sediment become entrained at a glacier's base through several mechanisms. Freeze-on, the refreezing of basal meltwater around rock fragments, can incorporate material directly into the ice at the bed. Where subglacial water moves into a slightly colder region and refreezes, it can trap sediment and small rocks in the growing ice, lifting them off the bed and into the basal layer of the glacier. Where the glacier flows over bedrock that has been fractured by previous glacial action, it can pluck loose blocks directly from the surface, incorporating them into the basal ice. Once frozen into the glacier's base, these rock fragments are carried forward with the ice, grinding against the bedrock below as the glacier moves. The contact between a rock embedded in the glacier's base and the rock surface beneath is where glacial erosion becomes most direct and most powerful. The embedded rock acts as a tool. As the glacier slides forward, the fragment is dragged across the bedrock surface, scratching it, scoring it, polishing it, grinding it down with a force determined by the weight of the ice above. Over years and decades, this process produces the characteristic features of glacially eroded rock, the smooth, polished surfaces that gleam in sunlight, marked with parallel scratches and grooves called striations that record the exact direction in which the glacier flowed over them. Glacial striations are among the most direct and legible records of ancient ice movement. A striated rock surface tells you, with great precision, the direction the glacier moved. The scratches run parallel to the flow, their depth and spacing reflecting the size and hardness of the embedded fragments that carved them. Where bedrock surfaces have been protected from erosion since deglaciation, striations can remain sharp and clear for thousands of years, a frozen record of the ice that once moved over them. The polishing of bedrock by glacial action is equally distinctive. Fine rock flour, the powdery product of the grinding of rock against rock at the glacier's base, acts as an abrasive, smoothing the bedrock surface to a degree that water erosion rarely achieves. The characteristic sheened, almost glassy surface of glacially polished rock is a hallmark of formerly glaciated terrain, visible on exposed bedrock outcrops throughout the mountain ranges and polar regions of the world. But the glacier does not only scratch and polish. It also deforms around the obstacles it encounters, and this deformation involves a process that is among the more elegant examples of physics operating at a material interface. When a glacier's base encounters a bump in the bedrock, a protrusion in the rock surface that the ice must somehow move around or over, it faces a mechanical challenge. The ice must deform to accommodate the obstacle, and it can do this in two ways, which often operate simultaneously. The first is enhanced basal creep. We have already discussed creep as the fundamental mechanism of internal ice deformation, the slow, continuous change of crystal shape under stress. At the glacier's base, where the ice is in contact with bedrock bumps, the stress concentration around those bumps drives locally enhanced creep. The ice deforms more rapidly in the vicinity of the obstacle, flowing around it and past it as the pressure drives accelerated crystal reorganization. This enhanced creep is the dominant mechanism for ice moving around obstacles of intermediate to large size, bumps too large to be accommodated quickly by the other mechanism available. That other mechanism is regulation. Regulation is one of the more physically striking phenomena in glaciology, and understanding it requires recalling a property of ice that we touched on earlier: the melting point of ice decreases with increasing pressure. Ice that is stable at a given temperature can be melted by applying pressure to it, even without any addition of heat. When a glacier's base presses against a bedrock bump, the pressure on the upstream side of the bump, the side facing the direction of ice flow, is higher than the pressure on the downstream side. On the high-pressure upstream face, the locally elevated pressure depresses the melting point of the ice. If the temperature of the ice is close to the melting point, as it often is at the base of a temperate glacier, the ice on the upstream face of the bump melts under this pressure. The meltwater produced flows around the obstacle, through the thin film at the ice rock interface, from the high-pressure upstream side to the lower-pressure downstream side. On the downstream side of the bump, the pressure is lower. The depressed melting point effect is weaker. The water arriving from the upstream side now finds itself at a temperature below the local melting point, and it refreezes, releasing latent heat as it does so, that heat being conducted through the rock of the bump back to the upstream face where melting is occurring. This cycle, melting under pressure on the upstream face, flow of water around the obstacle, refreezing on the downstream face, is called regulation slip. It allows the glacier to move around small bedrock obstacles without any macroscopic fracturing of the ice, simply by cycling water around the obstacle in a continuous loop. The latent heat released on the downstream side is conducted through the rock bump and used to drive further melting on the upstream side, making the process self-sustaining as long as the glacier continues to press against the obstacle and the ice remains close to its melting point. Regulation is most effective for small obstacles, those small enough that heat can be conducted through them quickly enough to maintain the cycle. For larger obstacles, the distance over which heat must be conducted is too great, and regulation alone cannot accommodate the ice flow. Enhanced basal creep takes over for the larger obstacles, while regulation handles the smaller ones. Together, these two mechanisms allow glacier ice to move past a rough bedrock surface with a fluidity that the rigidity of ice at everyday scales would not suggest possible. And as the ice moves past these obstacles, through creep and regulation, through sliding and deformation, the rock fragments frozen into its base are continuously abrading the rock below. The grinding produces rock flour that is carried away in the basal meltwater, emerging at the glacier's margin in the characteristic pale, silted streams that flow from beneath the ice. The larger fragments embedded in the basal layer leave their deeper scratches and grooves. And the bedrock surface is shaped, millimeter by millimeter and century by century, into the polished, striated, rounded forms that identify it, even long after the ice has retreated, as a surface once covered by a glacier. The material eroded from the bedrock does not simply vanish. It is carried forward in the ice, in the basal layer, in the inglacial debris bands, on the surface moraines, transported by the glacier's flow toward its margin. The distance over which a glacier can transport debris is extraordinary. Rocks picked up at the head of a mountain glacier may travel tens of kilometers to the glacier's terminus. Debris entrained at the base of an ice sheet may be carried hundreds of kilometers before it is finally deposited as the ice melts. This transport capacity gives glaciers an importance in the redistribution of Earth's surface materials that is difficult to overstate. The erratic boulders that sit incongruously on plains far from any mountains, great lumps of rock whose type matches nothing in the local geology but corresponds precisely to rock formations hundreds of kilometers away, are the calling cards of ancient glaciers. They were plucked from bedrock outcrops far from where they now rest, frozen into glacial ice, carried forward through the ice's slow movement, and finally deposited when the glacier melted, left sitting on the landscape as monuments to a journey that took thousands of years. Some of these erratic boulders are enormous. Boulders weighing hundreds of tons, sitting on flat plains with no explanation in the local geography, have been traced back to source areas hundreds of kilometers distant. The glacier that carried them is long gone, but the rock remains, a tangible, holdable piece of evidence for the reach and the power of ice that once covered landscapes now entirely free of it. The glacier, in this sense, is not just an agent of erosion. It is an agent of redistribution, moving the material of the Earth's surface across distances and in directions that no other geomorphic process could achieve. It takes rock from mountains and deposits it on plains. It carries the chemistry of one geological formation into an entirely different one. It mixes, transports, and rearranges the surface of the Earth with a thoroughness that persists in the landscape for millions of years after the ice itself is gone. Ice and stone, in the end, are not simply in contact at the glacier's base. They are in a relationship, slow, forceful, and utterly transformative, that has been shaping the continents since the first great glaciations of Earth's history. And in the cold and the pressure of the subglacial world, that relationship continues, one abraded grain of rock flour at a time. When a glacier finally retreats, when the climate warms enough that melting outpaces accumulation and the ice pulls back from the landscape it once covered, it does not leave behind an empty, featureless plain. It leaves a record. Scattered across the newly exposed terrain are the marks of everything the glacier did while it was present. The polished and striated bedrock we have already described. The erratic boulders carried from distant sources. The moraines, ridges of deposited debris that trace the glacier's former margins like the outlines of a receding tide. And threading across the landscape, sometimes for dozens or even hundreds of kilometers, long, sinuous, narrow hills that rise gently above the surrounding plain, following routes that seem almost purposeful, as if they were built rather than formed. These are eskers. An esker is the cast of a subglacial river channel, the sediment that was deposited within an inglacial or subglacial conduit as it carried meltwater toward the glacier's margin, left standing as a ridge when the ice around it melted away. The channel itself is gone. The ice that formed its walls has long since vanished. But the sediment that accumulated within it, sand and gravel deposited by the flowing water in the same way that any river deposits sediment in its bed, remains, now exposed on the surface as a raised ridge that follows the path the subglacial river once took. Eskers are among the most striking landforms produced by glaciation, and they are also among the most informative. Their form encodes information about the subglacial drainage system that produced them, the direction of flow, the dimensions of the conduit, the velocity of the water, the nature of the sediment being transported. A wide, gently curving esker suggests a large, slow conduit. A narrow, steep-sided ridge suggests a smaller, faster-flowing channel. Branching esker systems record the arborescent drainage networks we described in the previous chapter, their tributaries converging on main ridges just as the subglacial channels they represent converged on the main drainage arteries of the glacier. In some regions, esker systems extend for extraordinary distances. In Finland and Sweden, eskers from the last glaciation run for hundreds of kilometers across the landscape, tracing the subglacial drainage of the Scandinavian ice sheet in lines so long and continuous that they have historically served as dryland routes through otherwise boggy terrain, natural highways left by the ice. In Canada, esker networks fan out across the boreal landscape of the Canadian Shield, their ridges rising above the surrounding lakes and muskeg, the skeletal remains of a drainage system that operated beneath kilometers of ice for thousands of years. Standing on an esker is a particular experience. You are standing on the bed of a river that flowed in complete darkness, beneath an ice sheet, perhaps 10 or 15,000 years ago. The gravel beneath your feet was transported by that river and deposited here as the water slowed. The ridge you are standing on is the shape of the channel that river occupied. Nothing remains of the ice that surrounded it, but the form of its drainage persists, raised above the plain, readable by those who know what they are looking at. The glacier is gone, but the record remains. And records are what we turn to now. Because ice, in its long and patient existence, does something that no other substance on Earth does quite so completely or so precisely. It remembers. Each year's snowfall, accumulating in the glacier's upper zones, traps within it a sample of the world as it existed at that moment. Not a metaphorical record, a literal, physical, chemical record, preserved in the ice with a fidelity that can be read by scientists with the right instruments, extracting information about climates and atmospheres and volcanic events and ocean temperatures from ice that formed thousands or hundreds of thousands of years ago. The primary tool for accessing this record is the ice core. An ice core is exactly what it sounds like, a cylindrical sample of ice drilled from a glacier or ice sheet, extracted in sections and brought to the surface for analysis. In the thickest parts of the Antarctic and Greenland ice sheets, drilling operations have retrieved ice cores that extend more than 3 kilometers below the surface, their deepest sections containing ice that formed more than 800,000 years ago. Each meter of that core represents years, decades, sometimes centuries of accumulated snowfall, compressed and transformed into glacial ice, and preserved within it, exactly as we have described throughout this journey through the glacier's interior, are the tiny bubbles of ancient air, the layers of volcanic ash, the particles of wind-blown dust, and the chemical signatures that allow scientists to reconstruct the conditions of the past with remarkable precision. The air bubbles are perhaps the most extraordinary component of this record. When snow falls and accumulates in a glacier's accumulation zone, it traps air in its pore spaces. As that snow is buried and compressed into firn, and as the firn is further compressed into glacial ice, those air spaces are gradually sealed off, cut off from the atmosphere above and preserved as discrete bubbles within the ice. The air inside those bubbles is, in the most literal sense, a sample of the ancient atmosphere, the exact mixture of gases that existed in the air at the time and place the snow fell. By analyzing the composition of air extracted from ice core bubbles, scientists can measure the concentration of greenhouse gases, carbon dioxide, methane, nitrous oxide, in the ancient atmosphere with a precision that no other proxy record can match. The results of these analyses have been among the most consequential in the history of climate science. They reveal a clear, repeated pattern across hundreds of thousands of years: greenhouse gas concentrations rising and falling in concert with global temperatures, through a series of glacial and interglacial cycles driven by variations in Earth's orbit. The ice core record of atmospheric carbon dioxide is one of the most reproduced graphs in all of science, a long oscillation across 8 glacial cycles, with concentrations ranging from about 180 parts per million during the coldest glacial maxima to about 280 parts per million during the warmest interglacials, cycling with a regularity that reflects the deep astronomical rhythms of Earth's orbital mechanics. And then, at the rightmost edge of the graph, at the point representing the last few decades, the line departs from all previous patterns, rising steeply to levels that have not been seen in the ice core record for at least 3 million years. That departure is measured in the same bubbles, in the same cores, using the same methods. The ice does not editorialize. It simply preserves what was there. The layered structure of the ice provides a chronology. In the upper sections of an ice core, annual layers can sometimes be distinguished visually, alternations of slightly different ice types corresponding to summer and winter snowfall, or to the deposition of thin layers of wind-blown material that vary with the seasons. Counting these layers downward from the surface gives an age for each section of ice as directly as counting tree rings gives an age for each year of a tree's growth. In the deepest, oldest ice, where annual layers have been compressed to millimeters or less and can no longer be distinguished individually, the chronology is established through other means, through the identification of specific volcanic horizons whose ages are known from other evidence, through the modeling of ice flow and accumulation rates, through the measurement of isotopic ratios that vary with temperature in predictable ways. The resulting age models for the oldest ice cores are not perfectly precise, but they are sufficiently well constrained to allow confident statements about the climate of the deep past. The volcanic horizons deserve particular mention. When a large volcanic eruption occurs, it injects sulfate aerosols and ash into the stratosphere, where they are distributed globally by atmospheric circulation and eventually deposited on the surfaces of glaciers everywhere. These deposits form thin layers in the ice, identifiable by their chemistry and, in some cases, by the presence of microscopic glass shards from the eruption that can be matched between ice cores drilled at different locations around the world. A major eruption leaves its signature simultaneously in Greenland and Antarctica, in the ice caps of the tropical Andes and the high-altitude glaciers of Tibet. These matched volcanic layers serve as absolute time markers, allowing scientists to correlate records from different parts of the world and to calibrate the age models of individual cores against independently dated events. The eruption of Tambora in 1815, of Krakatoa in 1883, of Pinatubo in 1991, all are recorded in the ice, their sulfate signatures visible in cores drilled from glaciers that were accumulating snow at the time. And so the glacier, through its internal layering and its preserved bubbles and its chemical record, becomes a library, one that has been building itself, undisturbed, for as long as the ice has been accumulating. A library written not in words but in chemistry and physics, in crystal structure and isotopic ratios, in the concentration of gases in tiny bubbles and the acidity of individual annual layers. The patience required to read it matches the patience required to build it. Now, the glacier keeps one more category of secrets, ones that are less about memory and more about behavior. About what happens when the systems we have described throughout this entire journey reach a point of instability. When the quiet, continuous processes of drainage and flow and erosion are suddenly, violently interrupted. Glaciers can flood. Not in the ordinary sense of meltwater streams swelling during summer, that is expected, predictable, managed. Glacial outburst floods are something categorically different, sudden, catastrophic releases of water that had been accumulating in subglacial or ice-dammed lakes, released all at once through drainage pathways that open with terrifying speed and discharge water at rates that can exceed the flow of the world's largest rivers. The mechanism of a subglacial outburst flood, called a jökulhlaup in Icelandic, a word that has been adopted into the international scientific vocabulary for its precision and its resonance, is a study in the instability of ice-dammed water systems. A subglacial lake, or a lake impounded behind a glacier's margin, accumulates water over months or years as meltwater and precipitation fill it. The ice dam that confines the water is not infinitely strong. As the water level rises, it exerts increasing pressure on the base of the ice. At some critical level, the water pressure becomes sufficient to lift the ice, to raise it slightly from the bed and open a pathway for water to escape. Once that pathway opens, even narrowly, the flood dynamics become self-reinforcing in the most dramatic way. Water flowing through the newly opened pathway generates friction and carries thermal energy that melts the ice walls of the conduit, enlarging it. As the conduit enlarges, more water flows through it. More water means more heat, more melting, faster enlargement. The discharge increases exponentially, from a trickle to a torrent to a catastrophic flood in a matter of hours. The water beneath the glacier, finding its pathway suddenly opened, surges forward through the subglacial drainage system. The flood does not travel simply. It can alternate between sheet flow, spreading broadly across the bed as a pressurized film, and channel flow, concentrated into the conduit system. Where the flood path encounters basins or depressions in the subglacial topography, water may pond temporarily, building pressure before continuing forward. These zones of ponding affect the flood's behavior, modulating its discharge, potentially routing it in unexpected directions. Subglacial floodwater can travel remarkable distances beneath the ice before emerging at the glacier's margin. Floods originating from subglacial lakes far in the interior of an ice sheet can travel tens or hundreds of kilometers through the subglacial drainage system, emerging at the margin as a roaring outpouring of turbid water laden with sediment, carrying with it the evidence of the flood's long subglacial journey. The drainage network through which the flood passes is permanently altered by the event. The enormous water flux melts conduits far larger than would be sustainable under normal meltwater inputs. After the flood, these oversized conduits are gradually closed by ice creep, but their geometry and location may influence the drainage patterns of subsequent seasons, the flood reorganizing the subglacial drainage system in ways that persist long after the flood itself has subsided. Subglacial drainage systems, we have noted throughout this account, are capable of self-organization, of developing efficient channel networks from initially distributed systems under the right conditions of water input and ice geometry. But this self-organization is not a smooth or monotonic process. Under changing water inputs, the drainage network can exhibit complex, nonlinear behavior, pressure patterns that oscillate, systems that switch between drainage states, instabilities that develop and resolve on timescales ranging from hours to seasons. These complex dynamics mean that predicting the behavior of a glacier's drainage system under changing climate conditions is genuinely difficult. A glacier that is receiving more meltwater than before may not simply speed up in proportion to the increased lubrication. The drainage system may adapt, developing more efficient channels that offset the increased water input with improved drainage, maintaining basal pressures and sliding speeds at levels not very different from before. Or the system may be overwhelmed, with water inputs exceeding the drainage capacity and producing sustained high basal pressures and significantly increased velocities. Which outcome occurs depends on details of bed geometry, ice thickness, and the history of drainage development that cannot easily be predicted from surface observations alone. The glacier, in this sense, retains a degree of inscrutability even after a century of scientific investigation. Its hidden systems, the drainage network, the subglacial lakes, the thermal state of the bed, the mechanical coupling between ice and till, interact in ways that produce behavior that is not always predictable from first principles, that can surprise even well-calibrated models, that continues to reveal new phenomena to scientists equipped with ever more sophisticated instruments. And there is one final element to add to this picture, one that operates not in the cold darkness of the subglacial world but on the glacier's sunlit surface, and that connects the glacier's behavior to the biology of the very simplest living things. Glaciers are not sterile. This is not immediately obvious. The surface of a glacier seems, at first glance, like one of the more inhospitable environments on Earth, cold, UV exposed, nutrient poor, subject to repeated melting and refreezing. And yet it supports life. Not abundant, complex life, but microbial communities that have adapted to exist on and within the ice, exploiting the thin films of meltwater that form on the surface during the summer season, drawing energy from sunlight and from the trace nutrients deposited by wind and dust. These surface microbial communities include cyanobacteria, algae, and a variety of other microorganisms, and they are more consequential for the glacier's physical behavior than their microscopic scale might suggest. Living cells are dark. Biological material on a glacier's surface, whether it is algal blooms spreading across the ice in summer, or the accumulation of microbial biomass in the pores of surface snow, absorbs more sunlight than clean white ice or fresh snow. It reduces the albedo, the reflectivity of the glacier's surface. Where the surface is colonized by microbes, more solar radiation is absorbed rather than reflected back to space, and the rate of melting increases. This biological darkening of glacier surfaces is not a minor effect. On the Greenland ice sheet, the so-called dark zone, a broad region of the ablation zone where biological and non-biological darkening combine to dramatically reduce surface albedo, has been expanding in recent decades, contributing to accelerated surface melting that affects the overall mass balance of the ice sheet. The microbes are not passive inhabitants of the glacier. They are active participants in its physical evolution, their collective darkening of the surface feeding back into the rate of melting that in turn shapes the liquid water environment they inhabit. It is, in a small way, a fitting conclusion to this long journey through the life of a glacier. We began with a snowflake. With the patient accumulation of layer upon layer, the compression of snow into firn and firn into ice, the slow recrystallization of the ice as it was buried deeper and subjected to greater pressure. We followed the ice as it began to move, through creep and basal sliding, through the deformation of crystals and the sliding of glaciers over bedrock. We descended into the subglacial world of water and rock, into the hidden drainage systems that route meltwater in directions that defy ordinary intuition. We traced the erosion of bedrock and the transport of debris across hundreds of kilometers, the recording of ancient climates and ice cores, the catastrophic release of stored water in glacial floods. And at the end, we find microbes. Living things, some of the oldest forms of life on Earth, quietly colonizing the surface of the ice, absorbing sunlight, releasing pigments, darkening the glacier's face, and in doing so, contributing in their small way to the glacier's response to a warming world. A glacier is a system. Not simply a mass of frozen water, not merely a geological feature, not only a climate archive or a hydrological actor or an erosional force, but all of these things simultaneously, interacting with each other and with the atmosphere and the ocean and the biosphere in ways that are still being understood. It begins as snow, and it ends as the sea. And in between, it contains multitudes.